Hello, everyone, and thank you for attending today's webinar, Smallest Precision Cycloidal Reducers, brought to you by Design World Magazine and DieQua. We would like to thank our presenters, Tom Kahn and Roberto Vasquez, for being here today. I'm Leslie Langnaugh, Managing Editor at Design World Magazine, and I'll be your moderator. Just a couple of housekeeping details before we get started. You will see several boxes on your desktop which you can move around to suit your preferences. A couple of the more important boxes are the Q&A box, which is where you will enter your questions, and you will be able to enter these questions at any time during the presentation. We will answer them during the Q&A portion of the presentation, which will be at the end of the webinar. Another box to note is the additional resources. This box contains links to websites for more information on this subject. And we also have a tweet box, which is where you can tweet interesting or key points made by the presenters. There's a list of hashtags for you to use. And now I'd like to introduce our presenters. Tom Kahn's educational background includes studies at Indiana University, Bloomington, Indiana, University of South Carolina, Daniels Center for Behavioral Studies, DeVry University Electronics, and Upton College Business Management. His professional career spans more than 30 years of experience in factory automation, working with major manufacturers of machine controls, providing motion systems with servo and stepper motors and variable speed AC and DC motor control systems. He has directly sold and supported many motion solutions to a diverse range of industry and automation segments. Tom's product management experience includes working with internal and external sales groups and channel partners to develop strategies and programs. His hands-on involvement with product training and joint sales activities has resulted in significant sales opportunities to OEM and aftermarket opportunities alike. Roberto has been an application engineer at DieQua Corporation for 9 years. His background is mechanical, but over the years he has learned more and more about AC induction type motors, servo and stepper motors, as well as simple DC brushless type motors. Roberto helps companies move through the application process, selection process of gearboxes and gearheads to meet their expectations. Tom and Roberto will both be available to answer your questions after the presentation. And now I'm going to hand over the webinar to Tom.
Leslie, thank you very much, and we appreciate the opportunity to be here. Good afternoon, everyone, and thanks for being part of our presentation webinar on our Spinea product series, the miniature cycloidal reducers. As Leslie mentioned, my name's Tom Kahn, and Motion Products Manager with DieQua. As Leslie mentioned, Roberto Vasquez is our Technical Support Supervisor for the DieQua Mechanical Gearing Solutions. This afternoon, we're going to try and keep the presentation succinct and on track. Hopefully keep it to 35 or 40 minutes so we open up the opportunity for questions. The material that we're going to be covering this afternoon, talking about the cycloidal reducers' attributes, their capabilities, what are the different housing configurations that are available to work with a myriad of different applications. What are some of the typical applications that this type of product comes into play? We're going to take a look at their construction. What is it about an ultra-low or zero backlash cycloidal reducer that lends itself to being a very compact, well-integratable solution, again, with zero backlash capability? Please feel free to ask us any questions at any time. We look forward to responding to you. So I'd like to open up the presentation and ask you to respond, if you would please. In thinking about your present design, what would you say as an individual and organization you prefer? One, to design all of the components internally as well as produce them in-house, or typically do most of the design, produce some of it internally, but you might consider it to outsource. Third, We do some of the components, and we do produce those inside, or you typically outsource everything. So we'd look forward to your feedback on that. If you'd click on one of those 4 and hit submit, we'll look forward to your feedback. So it's kind of interesting looking at the response that most of the components are designed internally. And as we explain the construction of the cycloidal reducer, you might understand how that question can be influenced by the capability and capacities of the cycloidal units that we're going to be talking about. So when we look at the 4 families that make up the twin spin product group, all of them share similar attributes. You can see the 4 different housing styles that are available, and we'll talk a little bit more about the capabilities of each of them. But what makes them very unique, they are all 0 backlash. Our most compact one has a robot flange that's as small as 50 millimeters in diameter in a small 55 by 55 millimeter housing. That's the M series. Because these units also include the bearing support members that directly support the output flanges, they have superior capability to handle the actual mechanical load of the application, eliminating some of the mechanical design elements that you might normally have to fold into the construction to help bear the loads that these reducers will typically see. So when we first talk about the M series, this is the smallest of the 4 families. As I mentioned, it's a small 55 by 55 millimeter unit. Torque capacity up to 18 Newton meters with a peak of about 36. So here we have a small compact package that in very compact small production machining type applications or robotics lends itself well to being integrated into a very tight package. The T series is a cylindrical design, solid output flanges both on the front and back side. The cylindrical housing lends itself well into robotics where we need to reside within inside between the second or third joint that sits resident into the structure of the actuator. Also, because it is a very compact package where high torque in a small, dense package is an area that it exceeds at. Of the 9 sizes that are available, 4 of them are available from 60 up to 110 millimeters and all the way up to 300 millimeters. The E series, similar in construction to the T, but it incorporates a solid steel flange for direct mounting into the application. So if you had an application where you needed to mount the reducer and handle heavy tilting moment with a direct mount on the housing, this facilitates a much more streamlined integration into the application. And in this size unit, there are 7 sizes available, and 3 of them are below 110 millimeters. And then the H series is the hollow bore version that's available with hollow bore configurations from 13 millimeters up to 65 millimeters. Again, with that external mounting flange, this gives you superior axial, radial, and moment capacity. When we look at the H series as an example, pardon me, the tilting moment has a maximum of up to 4,400 Newton meters. When we look at the E series, again, because they're similar designs, also up to 4,400 Newton meters. The T-Series offers the highest capacity, and that is up to 12,000 Newton meters. And so you see that the designs themselves lend their capability into enhancing the application. So when we look at where do these reducers typically become utilized? And this is just a brief overview of where the twin spin fits into many different market segments and applications. Some of them stand out more prominently than others. What all of these applications have in common is the demand for high precision and accuracy, smooth and accurate positioning, the ability to deliver increased moment, radial, and axial load support in a very compact package. When you look at these different market segments, there are multiple ways to solve applications, gear reduction applications. We found that our customers typically look for very small, dense solutions for integration. Pardon me. This is a cross-section of the E-Series reducer. You can see the integral flange that's shown in the graphic. Some of the key elements that all of the twin spin reducers share would be the steel housing, in this case with the mounting flange. Talk a little bit about the high-speed mounting shaft. This is a low diameter or small diameter input shaft. It offers low inertia on the input and speeds up to nominally 2,000 to 2,500 RPM with peak speeds of up to 4,000 RPM. Supporting the high-speed shaft is incorporated a set of dual taper roller bearings on both ends of that input shaft. So the solution is delivered with a complete bearing support structure. The interface is a direct connection to the motor. The additional taper roller bearings mid-center on that input shaft are the two eccentric cams. These develop the oscillating motion counteropposed to one another, and these are actually what drive the tricloidal wheels. The tricloidal wheels are what move in a planetary fashion, dynamically balanced 180 degrees from each other. They, as they're rotating, stepping around the inside of the reducer, they ride against and over the needle bearings. These are the elements that actually generate the torque force. Because both of the the tricloidal wheels move in a planetary moment, rotation, we have to take that slight oscillating movement and convert it to pure rotational force. The transformation cross facilitates that transition from oscillating motion to pure rotational force. Both output flanges are ISO 9409-1 standard, permitting direct connection and interface to any standard interface that's required in the application or out on the market. Lastly, to support those flanges, we have cross roller bearings on both flanges. This is where we get superior moment, radial, and axial capacity in a very compact package. Looks like we might have some technical difficulty here.
I'm seeing the video. Are you seeing it okay, Tom?
No, we're not seeing the video. So if I can explain what I hope everyone else is seeing, this is a sample of the larger twin spin reducer for sake of visualization. We've removed the front steel cover and replaced it with a machined acrylic surface. As the input shaft is rotating, you'll see the high-speed shaft turning. The taper roller bearings are supporting the input shaft. We then also see the transformation cross and the tricloidal wheel moving around counter rotation to the input. So this is how we actually generate rotational force. The next clip, again, I'm hoping everyone's able to see it. This is a close-up of the tricloidal wheel riding against, over, and stepping, if you will, against those needles. We maintain contact 50% of the time with those needles in a torque driving position. We never lose touch with those needles, which is why our torque capacities are so high for such a small packaged reducer. Next, please. The video that you're watching, I'm going to let Roberto explain through this, is a 3D vignette which demonstrates the construction of the twin spin as the unit is rotating. Roberto, if you would please.
So what we're noticing here on this third video, we have the twin spin construction for the T-Series. This is the unit has the compact housing where the flanges within the enclosure of the gearbox. The way this functions, as you might see in the video, your input rotation occurs at the center shaft. That rotates the eccentric bearings, which transfer the motion through the transfer bar, transformation cross, to then walk the cycloidal wheels against the needle bearings. The reaction force then drives the output flanges based on the number of teeth and the number of needles. There's a difference of 1. This oscillation motion causes the wheel to walk the perimeter, the circumference of the lobes, if you would. Each of them, as they're walking, transfer the torque in a rotational manner out the output shafts. So this is why your motor or your input would be on the center of the gearbox, and then you could then mount your output, whether it be on the left or the right side flange. They'll be counter-rotating because it's a reaction force from your input speed as it's walking the cycloidal wheel around the needle bearings. It's a reaction force, so what you'll notice is if you're going in with your input rotation at clockwise rotation, your reaction force would then be counter-rotating.
Roberto, thank you. So we have another general question for the group. Would you consider using a reducer that has radial, axial, and moment capacity without needing to add additional bearing components?
Has everybody had time to answer this question? Okay. Go ahead and move to the next one, to the results.
So split about 50-50. In the applications that we're going to take a look at, previous technology has required the designers to incorporate additional bearing structure. When presented with the capabilities of the twin spin cycloidals, because of that bearing structure, both for torque and for axial, radial, and moment loads, it's given them greater freedom to actually change the design and incorporate that support well within the reducer. One of the first applications that we're going to explore is a machine turning center, and here we have three different twin spin reducers here located up in the cutting head, position control on the trunnion across the bottom, and then the workpiece orientation control. What the customer was looking for was a solution that gave them higher mechanical capacities, but also the ability to have very smooth position and speed translation, because that directly impacted on their workpiece production. In this application's case, we utilized a 70 millimeter diameter, an 80, and a 110. Typical in the size 70 is the ability to generate 50 newton meters of nominal torque, moment capacity of up to 142 newton meters. Where the twin spin product really excels is that axial, radial, and moment capacity, and in this case, the radial capacity is 2.8 kilonewtons of capacity. In the part positioning, we're using the 80 millimeter size unit, and this generates up to 280 newton meters, and then the size 110 up to 122 newton meters. So here we have a very small, compact solution that integrates well into this application. In the dental industry, there has been an increased demand for more customized tooth prosthetics. And in order for that to have more of a natural feel and a fit, again, the twin spin utilized to deliver smoother positioning, which gives them the ability to produce a more refined surface, but also with the increased capacities of the reducers, the material can be changed from a zirconia type material to other more elegant type materials, more common in aerospace or that type of industrial application. So axial, radial, high moment capability, and in utilizing both the twin spin 50 and the twin spin 70, again, small, compact, high capacities, upwards of 1,400 newtons of radial, 1,900 of radial capacity, small package, easy to integrate into a small space. The issue that we typically run into in water jet applications is the speed and the force at which the cutting solution is presented out through the nozzle controls how well the finish of the cut is. And in the case of this application, we've utilized both the solid face units, also the hollow bore unit. One of the considerations here is to also address the reaction force that is presented by a water jet type system. One of the considerations noted here is the low angle transmission error. In other words, we are very precisely aligning and positioning as we're passing the cutting nozzle through space to deliver a superior product.
One thing that would help you accomplish such motion would be the zero backlash in the reducer. It's able to give you the hysteresis, repeatability, and overall loss motion. So you have a predictable output based on where you anticipate your motor to be. Through the gear ratio, you basically have the zero backlash result, and then any torsional stiffness would be reinforced through the components of the reducer, giving you the utmost in precision.
Thanks, Roberto. Change a little bit in the application. Here is a version of an automatic guided vehicle or also an automatic guided cart. The areas that the twin spin solution plays well in this application is both in steering and propulsion. Because of the compact design, the ability to support considerable radial load within the housing of the reducer lends itself to being integrated into a very tight, compact package. There also is the use of our drive spin product, which is the cycloidal reducer integrated to the front end of a brushless DC motor. This helps to also shorten the axial length, permitting a much tighter integration within an application.
All right, if we go ahead and take a glance at a reducer's housing, and here's a question for everybody. If you take a glance at the reducer's housing, you'll notice the robustness, how well it's constructed. Great for ideal bearing support. From these 4 items listed below, I'd like to pose a challenge, see if you could identify it. Which 3 are prime examples of the benefits that having a strong bearing support would offer? So what are the benefits you would get in having such a high bearing supported unit? We'll give you guys a second. Okay. You guys need a little bit more time, or maybe rephrase the question. What are some benefits in having all the bearings in the gear reducer? All right, let's see the results. Right, so providing a high torque dense transmission, what that's going to do is not only does it transmit in a small package a great deal of torque, but it's able to do so because there's a great deal of bearing support within the unit. Furthermore, because it has the bearing supports within it, it could actually handle not only the reaction forces of the components internally, but it could actually support the outside influence, whether it's radial, axial, or in what we consider a bending moment or tilting moment, would be the off-center axis, axial and radial compounded together to give you a tilting moment. Also, yes, precision. So having bearings support the internal mechanical components will give you the ability to avoid deflection, and also if you have very tight tolerances within your components, you don't lose the benefit of having the tight tolerances if your bearings help you support the units that you're transmitting with.
Thank you, Roberto. Little different application here. The issue was that we had a very limited amount of space to assist in actually applying with a adhesive the drinking straw to the exterior of the aseptic carton. What lent itself, we used the TS80 to help position the applicator straw element to keep it in line, as the packaging size might vary slightly from different packaging type containers. And so the unit that we selected was the Twin Spin 80, or an 80 millimeter diameter unit, also with that integral flange that gave us high torque and tilting capability Also, by the nature of the application, it also delivered long life. Here we have a positioning solution that places the target object into the particle stream collider. The nature of these applications demand micron-level positioning because they have to adjust and control where the actual scientific application is being delivered in the beam. And so a set of the twin spin 70s did a superior job of consistently and repeatably positioning the scientific target into the beam. A few of the other applications won't go into a whole lot of detail, but each of these have inherent issues with reactive forces and require very high precision, high repeatability, and accuracy either for an automated remote weapon system or for the laser designation or camera positioning system. A few other applications similar are remote surveillance systems that would exist out in the field. Simulation, typically hydraulics are used in the flight simulators. The cycloidal reducers eliminate the issues of a hydraulic power pack and deliver high performance with an electromechanical solution. The military robot for surveillance or IED disposal, compact, high strength in a small package. Another application in communications type applications for both fixed station or mobile applications, because of the mechanical capacities of the reducer, we are a good, compact, robust solution able to tolerate the military grade temperatures, -40 to +50 C. By the nature of the bearing structure, it also helps simplify the design of the tilt and pan on the dish or antenna positioning system. Additionally, no load starting torque, but also again high stiffness to resist buffeting from wind pressure. In this application, we're looking at a scanner. The typical applications in this are patient positioning, gantry control, and alignment. So in the case of a medical application, you want as low a noise signature from the gearboxes as possible to help support the mechanical load, high torsional stiffness, and again, a very low no-load starting torque to improve efficiency of the system, again, to hold costs down.
All right, let's take this down and pose another question here. While the units are very precise, and that we know, this nearly eliminates lost motion. How does the unit handle continuous duty, right? Because we're talking about a unit that's perfectly ideal for intermittent, precise positioning. How does this unit handle continuous duty? All right, so the question is, will it handle it well? Is it okay if it's limited input speed? Will it generate so much heat that an external fan is required? Is it such that because it's designed for intermittent duty, continuous duty will require special grease? Or will we expose it to continuous duty, but the end result will be their thermal expansion that will take effect and therefore decrease the unit's efficiency? give you guys a second, see if you could think that one through. All right. Perfect, right. So the unit could perform continuous duty if it is subjected to lower speeds and lower torques. So typically, because this unit is so high in precision, very low tolerances within the components to give it the utmost in loss positioning, efficiency typically on these units hovers around 73%, 75%, roundabout. The faster you would go, the more heat you generate. So the more thermal expansion within the unit would then cause things to kind of rub into one another a little bit more so therefore efficiency will drop as well. But in your case, if you run slower, lower torques, heat generation won't be such a concern. So yes, continuous could then be used. Or to handle the increased temperature, like somebody had posed here, special grease can be considered.
Roberto, thank you. So we've talked a little bit about applications, some of the reducer's capability. Briefly, I want to talk about how we typically interface a motor to the cycloidal reducers. The most common interconnection approach is direct connection. So we have an adapter flange that is sized specifically to the reducer and to accommodate the servo motor. Typically in this configuration, the diameter of the servo motor matches the input diameter for the reducer. However, there are instances where in a direct connection, because the motor might have a smaller diameter shaft, we incorporate an internal collet and clamp to the shaft. This is then drawn against the mounting flange, which is mounted to the reducer and is secured via a set screw, which pulls the shaft around the collet around the motor shaft. So in instances where we have a motor with a larger diameter output shaft, we incorporate using a zero backlash coupling, a mounting flange that permits the coupling to reside inside of it, and then a direct plug-in shaft to simplify integration. There are also applications where the customer needs to save space. Axial length may be a consideration or a concern, and so this reverse parallel wrap with a timing belt is a good solution to permitting connection between the motor and the reducer being a timing belt. In the four applications or integration techniques that we just looked at, that would be employed on the solid-faced output reducers. But because we also have some versions that are hollow bore that permit power, pneumatics, plumbing to be delivered right through the center of the reducer, it isn't appropriate to have the motor right in the way. So here we can see there's a gear type pre-stage available that permits the pre-stage interface to the servo motor that's offset onto the hollow bore reducer. There are other requirements occasionally where that integration needs to be via timing belt and a parallel offset, again, permitting free access through the center of the reducer. When we typically look at an application to understand the demands of it, how do we best meet your needs and the capabilities of the reducers? These 10 elements are the most common questions that we're going to ask for. The application worksheet also helps us to understand the dynamics of your application and how that might affect or impact the reducer. The information on the app worksheet also permits us to calculate both life and load capability, and it keeps the project sheet in one nice, neat, concise package. Everyone, we appreciate the opportunity to present our twin spin cycloidal reducers, and we look forward to your questions. Thank you.
Thank you, Tom and Roberto. Okay, everyone, so here's the opportunity for you to put in your questions if you have not already done so. And we'll begin the Q&A portion right now. So let's get started. One of the first questions here is, what is the efficiency of a cycloidal reducer?
Sure, I can speak to that. So like we had discussed earlier, the units have very tight tolerances, meaning that there's a lot of components with high preload being applied. As a result, the unit at base speed, so imagine 2,000 RPM at rated torque, based on those reaction forces internally, the unit is said to be 73 to 75% efficient. So then you might ask, well, what about it faster than base speed? The faster you go, the higher inherent reaction forces internally, as well as thermal expansion. So what that's going to do is going to create a great deal of force and thermal expansion. So your efficiency is probably going to dip down something like 50 or 60%. If you decrease your speed, then you're actually going to improve your efficiency closer to 80%. But keep in mind, there's a no-load running torque on the unit. So if you're getting closer and closer to lower speeds, your set efficiency will actually go closer to 60%. So around about 70 is your number.
Okay.
Good question.
The next question is, can a cycloidal reducer be run in a continuous mode of operation?
Yeah, so that's a very good question as well. As we had discussed earlier, the unit is ideal for precise intermittent positioning. You need to rotate 120 degrees, or you need to get from one point to the other point in a repeatable manner, right? So what these units are designed for, perfect for intermittent. But sometimes you have to operate in a robust manner where you could benefit from the increased tilting capacity or the high radial or axial capacity, and your speeds, they're not super aggressive, and your load is maybe within 80% of the rated torque. Yes, you could run it continuous.
Okay. Another question's come in. We use hundreds of stepper motors, NEMA 14 to NEMA 34 sizes. What would be the best match for these types of motors?
So typically, and that's a good question to ask, because we are always interfacing with either servo and occasionally step motor. In the case of the stepper motors, because they're the predominant area of their torque generation is from very low speed up to about 1,000 RPM. That's well within the speed bandwidth of the cycloidal reducer. As Roberto mentioned, the average efficiency of the reducer is about 70%. When we're interfacing with a step motor, the question comes to, well, at what speed will this become less efficient? And the answer is that it's consistent across that speed bandwidth at 70%. So when you get to a smaller NEMA 14, there might not be enough torque to handle both the burden of the application and the burden torque to drive the reducer. Whereas on a size 34, that certainly lends itself to a pretty wide range of the smaller reducers. So typically it would be, when we size these, we look to see what other mechanical beyond torque we have to consider the needs of the application. We'd certainly welcome additional data to see how we could help resolve the app for you.
Right. One thing to consider with the NEMA 14 is the no-load running torque for miniature series, the M series. You're looking at 4 centi newton meters, or you can see it as 0.04 newton meters. So you could consider that as a no load running torque, and so long as the ratio through the motor rated torque is enough, and consider the 70% efficiency, then yes, the NEMA 34 will be great, and then just reconsider maybe for the 14, make sure you have enough torque.
Okay. It was stated that all of the twin spin reducers are zero backlash. How do you explain lost motion?
Right. So, and that's without, right? It seems like if you're saying there's some lost motion, but then you have zero backlash, well, you can't have one or the other. And it comes down to terminology, right? Zero backlash means that all the components are in contact with one another at all times, right? So there's zero slap between the needle bearings and the cycloidal gears, the lobes on the cycloidal gear. At least 50% of the teeth are in contact at all times. So from that standpoint, there's no backlash. Lost motion comes up in a couple different manners. The primary manner is in torsional stiffness. So say you accelerate a component and get up to position, and you come to a very abrupt stop, there'll be some deflection in internal components, and depending on how stiff each component it is, you might have a spring effect or a hysteresis effect. And so being that our unit has a great deal of torsional stiffness, lost motion is kept at a minimum.
Okay. And do you have some examples or traits of a cycloidal reducer reaching its end of life?
Certainly. And that's a question that we hear occasionally in applications that where the customer demands to know what are the critical failure modes that might occur in an autonomous application or in robotics. Because the reducers are machined to a 1 micron, the internal components to a 1 micron tolerance, the efficiencies exist at 70%. As the reducer goes through operation, you will naturally get a wear-in of the components, and the backlash will remain zero. But as you approach the life expectancy, which is about 6,000 to 7,000 operational hours, again, depending on how close to load and performance capability the reducer is expected to deliver, what will typically occur is that efficiency will begin to improve because we now have less constrained motion. So the servo motor or the stepper motor, if the amplifier is able to monitor the power demand, the amplifier would begin to see a reduction in required current to effect a move. That would then permit the programmer to establish a bandwidth of, if I begin to see my current slackening off a little bit, I then also look at my repeatability. If that repeatability is beginning to open up and I'm demanding less power, that's usually indicative of wear occurring within the reducer. That's how we would recommend as customers are looking at their applications. Things do not fall apart, they don't shred, they don't break loose. It's those tolerances beginning to open up.
I fully agree with that, yes. And that's one of the benefits of this unit. Catastrophic failure will not have a failure in which the unit shears off, breaks off. It'll support the load. It'll just operate at looser tolerances or excessive heat.
All righty. Well, thank you again, everyone, for attending today's webinar. Thank you again, Tom and Roberto, for presenting it. Just as a reminder for everyone, you will receive a link to the webinar so that you can replay it at your convenience. It will also be posted on the Design World website. If you want to continue any conversations that you're having regarding this, There were various social websites and stuff that you could go ahead and continue the conversation. And in the meantime, thank you again, and we hope you all have a great rest of your day. Bye-bye.
Bye-bye. Thank you.
Bye.